Okay, Stats class, I think this might be the last video of the year. It is the chart for chapter 14. So, let's just go to it. We run two different types of inference for multiple regression. We have the overall F-test, which is for multiple regression. I guess that's kind of obvious. And then we have individual t-tests for multiple regression parameters, because each parameter would have its own t-test. So the null hypothesis for the overall F-test is you leave off beta 0, because the null hypothesis is saying all you need is beta 0. You put all the rest of them. So beta 1 equals beta 2 equals beta 3. Sometimes there's more, but we haven't done more this year. Sometimes there's not a beta 3, just 1 and 2, but it's all of the ones that are not 0, because this is basically saying all we need is the y-intercept. And then the alternate is at least one of these is useful, so at least one of these is not 0, and I'm going to write it as at least one coefficient, because that's what they're called. Does not equal 0. And it doesn't have to be all of them. And then if you want to know which one doesn't equal 0, that's what individual t-tests are for. So this, you have a t-test for each individual parameter. You have one for beta 0, one for beta 1, one for beta 2. If there's a beta 3, you have that too. Right? So sometimes there's 4 of these, sometimes there's only 3. And then the alternate is always just not equals for each one of them. So basically you write a separate set of hypotheses. These are for the y-intercept. These are for the first parameter, which is usually the slope. We'll write that down somewhere also, what these parameters mean. But basically, the alternative is that they're not 0. And you basically test all of these at once. When you're doing this with a computer, you put the same command in for all of it at once, and it spits out this output, which, by the way, we're going to do that on the back of this chart, the second page, if you're doing it digitally. So the conditions are the same for all 4 tests. Usually we just check them all at once. You have to have randomness. And as we talked about, these are the same conditions we had in chapter 12. Random sample for randomly assigned treatments. For normal, the thing that has to be normal is the residuals. And so we check the graph of the residuals, and that's a one variable type graph, not a scatter plot. You have box plot or a histogram or something like that. And it needs to just not be skewed. We're not going to be super picky about it, but not too skewed. Third one is independent. These should be so familiar to you by now, I hope. And if it's a sample, then n has to be less than 10% of the population. You just have one sample size to check. And then, or if it's an experiment, then randomly assigned treatments covers this. I'm going a little bit fast on this part because I feel like it's review and we've talked about it so many times before. So pause the video if you need to, right? Linear is the next one, and just like in chapter 12, we check a scatter plot. Usually it's a scatter plot of the residuals, but you could check either actually. If you're doing residuals, it's generally residuals with y hat on the axis. So residuals versus y hat, predicted y values. And it just needs to be not curved. We're not super picky about that either. Somebody asked me, could you do each individual explanatory variable and do separate residual plots for all of those? Well, you could, except that if they're categorical, that's kind of weird. So it would work for the ones that are quantitative, and usually that's not what's done. Usually what's done is use the predicted values. It's just easier to do one plot instead of many. And then equal variance. We saw that in the ANOVA chapter and in chapter 12, that we want the residuals spread out evenly and not really wide and really narrow. It's the scatter plot or the residual plot has to be evenly spread, not band. And if you want the fancy words again, this is homoscedastic and heteroscedastic. Every once in a while I have somebody who likes to show off by using those words. As long as you use them correctly, that's all right. And in honor of Pride Month, homo is good and hetero is what we don't want. What do you know? All right, so then we have calculations. Now I have some good news, and that is you will not actually need to use the calculations, but it just feels not complete to me to not fill this in. So I'm going to fill it in. You can leave it blank if you want to, because I am not going to make you do this. DF1 and 2, kind of like the ANOVA test. This is the mean square for the model and the mean square for the errors, which is residuals. SSM over DF1 and SSE over DF2. I just find it fascinating that this is basically ANOVA with scatter plots, and that's basically what we're doing. This is the y hat minus the y bar over k, and it's squared and added up. This is the y minus the y hat, and this is n minus k minus 1, like I said up there. And then the p-value, you would use the f-CDF of f and 999, something big, and k and n minus k minus 1, which is df1 and df2. So now I put all that because it feels more complete to me, but I'm going to tell you that what you're really going to do is use computer output. I am never going to make you use these formulas because it's the end of the year. We need a break. On the back, we're going to put the details of where to find everything on the computer output, and we'll get to that, so not quite yet. For the individual t-tests, the df is n minus k minus 1, same as the df over here. T is still d over seb like we've always done, and you'd have separate t's for d1, d0, and d1, and d2, and d3. You'd have like 4 of them, and you'd have to calculate them all, which I'm not going to make you do. TCDF is T and 999, and DF, except this one's always times 2 because it's always a not equals up there. We're going to do computer output on the back. Here's something I hadn't thought about till just now. In some years I did confidence intervals. We didn't do them this year. We just didn't get there. So we're not doing confidence intervals. You don't have to know that one. Never mind. Should have left it off. And then conclude, as you always have done, if P is less than alpha, then you reject. If P is greater than alpha, then you don't reject. And we're going to have our justification. I feel like some of this you could have filled in without my help because we've done it before. There you go. So now, I am going to make this easier on the quiz. So reward for people listening and not just writing, right? On the quiz, I'm not going to make you check conditions. I'm only going to ask you some multiple choice questions about the conditions, and I decided not to make you do the whole thing. I'm not going to make you do all these calculations. I will make you write hypotheses, answer some questions about this multiple choice, and make a conclusion from the computer output. So most of this middle part you don't need very much. On the back is the really important part. So there's a lot of stuff going on in here, and I'm going to say, let's talk about what the true formula looks like compared to the estimated formula. Now let's put those up at the top so that we can refer to them as needed. The true equation looks like mu y equals beta 0 plus beta 1 x1 plus beta 2 x2. That's the kind we did first, where we only had a quantitative and a categorical and 2 parallel lines. And then when we changed it to not being parallel lines, we added an extra piece. That was the x1, x2 interaction. And all of this repeats with the estimates, except now instead of mu y, we call it y hash. So this is the population in a sample, basically. Y hash, And these become b's instead of betas. So b0 plus b1 x1 plus b2 x2. Sometimes we stop there. Sometimes we add interaction. So that's what we're basing all of this on. So in our regression analysis, the computer output almost always tells you what the response variable is. I'm trying to decide if I'm going to leave that out on the quiz and make you just read the paragraph. I probably will, actually. But then if they put the versus thing, then you've got your explanatory variable number 1. And then you have your explanatory variable number 2. So usually when you're reading computer output, it tells you the variables right there at the top, which is kind of nice. Sometimes they give the equation to you also. I am not going to do that. So sometimes the regression equation is given right here. But I'm not going to give it to you because I want you to be able to find it. It will be this equation, the estimated equation that will be given there. I want you to know where to find the stuff right here. So that's what we're going to talk about. The coefficients, B0, B1, B2, B3, are always in order on this lovely chart. So this is B0, this is B1, this is B2, this is B3. B1 goes with X1, so this would be the name of X1 that the computer would put here. B2 goes with X2. B3, if there is one, or sometimes it's left off, goes with X1 times X2 because those are the only kinds we have learned right now. SEs, they just go with the one right next to them. So this is SE B0, this is SE B1, this is SE B2, this is SE B3. Notice in this unit we haven't been using these for anything. If I made you do confidence intervals, you'd need it. Otherwise, you don't really need it. But T divided by SEB is T, so that's where the T values come from. I'm not going to make you calculate them. I'm just going to say this is T0, T1, T2, and T3. It's the T values that go with the 4 individual T tests that we talked about on the other side. There's 4 different individual T values, and they're listed in the table right there. And then these are the P values for those 4 tests. P0, P1, P2, P3. These are the P values you need for the individual T tests. And I'm very likely to ask you to use those. So this is the important piece, and this is the important piece. You have to be able to look at this and write the equations, and you have to be able to interpret these P values and decide which ones are significant, which ones are not. Also, I might ask you to interpret some of this stuff. We don't use R squared adjusted this year, so just don't even worry about it. But S, you should know what S is. It's the standard deviation of the residuals, which is also called the typical or average prediction error. And I might ask you to interpret that. Predictions made by this model are off by this much. We've done that before. R squared, you already know what R squared is, but I'll say it again, is the percent of the variation in Y that is explained by the model, or technically explained by all those explanatory variables. And I might make you interpret that on the quiz. Analysis of variance, also called ANOVA. Yes, this is not the ANOVA chapter, but we're still doing ANOVA because you can do ANOVA calculations on the regression model. And I don't think I'm going to write all of this again. All of these formulas I wrote over here. Maybe I'll write it again just for completeness. That's fine. You don't have to if you don't want to. But GF1 is K, and GFK is the number. I forgot to write that before. K is the number of X's, number of explanatory variables that you've got. Maybe I should write that over here also. Number of variables. Residual df is n minus k minus 1. The total, we don't really need to worry about the total. Actually, I guess I will. It's n minus 1. If you add these together, the k's cancel, which is kind of nice. SS is the sum of the y hat minus y bars squared. and this is the sum of the y's minus y hats squared. And I'm going to draw you a picture of that. Maybe I'll do that at the bottom for people that want to keep listening. This is just the sum of SSM plus SSE, and you would use it to find, you did the explained over the total, you get R squared, but that's not important for this chapter. We're not going to make you do that. This is SSM divided by DF1. This is SSE divided by DF2. This is MSN over MSE. And then the p-value you would find by doing FCDF and all of that. And I'm not going to write that out again, but the most important thing that you need from this table is the p-value. This piece right here is the p-value for the overall f-test, which I will probably ask you to interpret. Overall f-test p-value. And one thing that I didn't put on here, but I did put in your notes, is when you reject, what does that mean? I'm going to just talk about it. If you reject this one, or if you reject this, you're saying that at least one coefficient is useful. So rejecting the null for the overall f-test means that the model is useful. Actually, I'll write that here. Reject means the model is useful for predicting whatever it is you're trying to predict. If you reject these ones, it means that specific coefficient is useful, or that specific explanatory variable that goes with that coefficient. So if you reject a null, it means slightly different things. Back to this, I'm going to do one more thing, two more things for you. One of them is to remind you that what these coefficients mean is something I might ask you about. So B0 is the y-intercept for the first group. This was in the warm-up, so you just did it, and I hope you got it right. For the first group, which is the group where x2 is 0. B1 is the slope for that first group, which kind of makes sense because if x2 is 0, these two pieces are gone. They're just not there. So then you have y-intercept and slope. That's easy. If you have an x2 equals 1, that's where you have the b0 plus b2. I had to stop and think about that. b2 is the extra added on, or the difference between the y-intercepts. So if you add these together, you get the y-intercept for the second group, which is the group where x2 is 1. And if you add the odd numbers together, 1 and 3, you get the slope for the second group. So that b2 and b3 are the extra added on to the y-intercept and the extra added on to the slope. I guess I'll do this. All right. The last thing I'm going to say, I know this is getting longer than usual for a chart video, but it occurred to me, I do know something more about this that's interesting, so if you're interested, here is what's happening with those subtracting and squaring and all of that. Let's say we have a scatter plot, we have a line of fit, we have, I'm going to pick a point and say this point has this residual, so we have our y, the actual y value, and then we have our predicted y value, which is y hat. I don't think I've drawn this picture for you before, so I've got to a few more dots, but I gotta just say it at least once this year. In the middle, we have our mean y value, which actually that would be the population one, so maybe I shouldn't say that, maybe I should call it y bar. So we're talking about the sample right now. Y bar, this distance right here is the distance between y hat and y bar. So like if we didn't have a regression model that was useful, we would just use y bar. We would just use the average y to predict. This piece is the part of the variation that's explained by the line. So the line is telling us that we can do a better prediction than this. We could go up here and make a better prediction, right? This is the good variation right here. And if you subtract the y hats minus the y bars and square them and add them all up, you get, you know what, I wrote this wrong, this is y bar. You get the good variation, right? If you take this little piece, which is the residual, It's the unexplained variation. It's the variation that is not explained by the line. And that's the bad variation that we can't really do much about, but it's bad. And then this here is the total variation. So if we take all of these and square them and add them up, that's the sum of the squared residuals, which is the bad variation. We're trying to reduce it as much as possible. But if we add them together, we get the total variation. And if we do explained divided by total, we get R squared. And I just think that's fascinating. So a little extra bonus thing for those who kept listening. Thank you for keeping listening. Technically, that's SSM, the sum of squares for the model, divided by the sum of squares total, which comes from these two spots on the table. You could find R squared by dividing those two numbers if you wanted to. That's how the computer does it. And how it's related to R is more complicated, but it is the same as the square of R. So I find this fascinating. Hope you did too. Last little thing I thought I should teach you today. So after you finish this, there is a practice quiz on Desmos. Finish that up next, and then take the quiz, and then finish your project. And that is all that we are doing this year. Thanks for listening.